So we've learned how to find the volume of a rotational solid. That's what it means by a rotating curve, right? So these will be rotational solids only using the disk method and the washer method, which of course are really the same method. It's just that the disk method is when there's no hole in it, and the washer method is when there is a hole in it, right? But there's another way to do this, and it's actually sometimes more efficient way. Students tend to be wary of it. They think it's more difficult than the disk and washer method. It isn't. It's actually just about the same difficulty. It's just a different way of thinking about it, and that can present a little bit of a challenge. So you take your region and you're rotating it. In this case, we're rotating around the y-axis. And you can see that right here. We're rotating around the y-axis. So we take that region and we rotate around, and we've built this kind of solid, right? Now, we could cut across it using the washer method because there's an obvious hole down the middle of this. So that means we would use the washer method. But another way we can think about it is that there's a stacking cylinders inside of this. Now, what do I mean by that? Well, if you flip to the next page, we'll be back to this page in a minute, you can see that solid is formed by concentric nesting cylinders inside. So it looks actually a little bit like how it would look on a pottery wheel. So if you can imagine, this was a piece of clay on a pottery wheel and it was spinning around, and you could form this up, and you would see these different ridge lines, and those are cylinders that are nested inside of each other. And if you let the number of cylinders you have go to infinity, right, the more cylinders you have, the smaller those ridges are, right? They're tinier and thinner cylinders fitting into this space. And if you let them go to infinity, then of course you've found the volume of the solid. Now, you've seen this before if ever you've seen children's nesting toys, which I particularly liked playing with as a child. These kind of cups that nest inside of each other. Cups that nest inside each other are an example of this, right? Because they're nesting inside and then they create a volume of them themselves, right? So you can figure out the volume of the solid that they form by finding the volume of each of them. Now, of course, these are also stacking, which isn't quite the same thing, but you get the idea. I actually have an example of a kind that doesn't stack here at home with me. My cookie cutters. So I have these cookie cutter rings, and you can see that each one of them forms a cylindrical shell, right? So it's a cylinder, and they nest inside of each other to form the volume of the solid altogether. And that's what you're doing. You're looking at these nesting cylinders inside of each other. Cylindrical shell, cylindrical shell. You're just letting the number of cylinders go to infinity, but they don't sell that kind of biscuit set. I'm limited to whatever they've got here. Okay, so it forms this volume altogether. And what you're going to do is you're going to add up the areas of each of the shells, the surface area of the shell. So I'm particularly interested in the surface area of that cylinder part. I don't care about the top and the bottom. They're open, so we don't have anything there, but we do have a cylindrical surface. All right, so let's go back a page. Let's remind ourselves about the area of a cylinder. Area of a cylinder, and I only want the surface part, the lateral surface. So let me say lateral surface area. That means the side, right? Not the top and the bottom. So the lateral surface area of a cylinder is, let me grab it from Google so you guys believe me. It's 2 pi RH, right? Because the circumference of the circle times the height. The 2 pi r squared gets you the area of the top and the bottom of the cylinder, which we don't care about. We only care about the 2 pi RH. As a matter of fact, I could probably look up lateral surface area of a cylinder, and it'll probably tell me 2 pi RH. Maybe? Yeah, there you go. So the lateral surface area, that's the side part, not the top and the bottom. So it's 2 pi RH. Why does that help me? Well, because what I want to do is find the surface area of all the cylinders and stack them up. Okay, well, let's look at what one of these cylinders looks like. So if you have this cylinder right here, it has 2 pi, it has a radius and it has a height, and then of course it has a thickness. The thickness is right here, which if you look down, here, let me make a little rectangle out of what we're doing. Because what we're doing is taking a rectangle and then swinging it around and forming that cylinder. That's how you form these cylindrical shells. If you look back at the region right here, you can imagine we have this kind of, well, this one's pretty high up there. So it's like this. We're taking a rectangle here. We swing it around the axis of rotation and it forms a ring, right? It forms a cylindrical shell. Okay, so if I have that rectangle swinging around and it forms a cylindrical shell, I've got a thickness that's dx, right? Dx because that's the x-axis down below right there. So that's a thickness in terms of x. I start at the innermost ring here and I end up at the outermost ring. So I want to start here at x equals a and work my way out to x equals b. So right here is the start and over here is the end. Right, you're working your way from the innermost ring to the outermost ring. Sorry, I got my rings all messed up there. All right, so you have your axis of rotation going down the middle. Beep. Sorry, I bumped the thing. And I go from the innermost ring of A to the outermost ring at B. X equals B, I should say. All right, now the fun part. I need to find the radius and I need to find the height. Now the height is actually pretty easy. The height is based on the fact that this was part of a ring to begin with. So this right here is your height. That's f of x, right? That height. So that's the same f of x down here. And then you need your radius. Your radius goes from your axis of rotation out to that rectangle. That's your radius. The distance from the axis of rotation out to whatever ring you're talking about. That would be the radius. Right? And that gets us the surface area times the thickness, right? Because the dx is the thickness of your shell, your cylindrical shell, which in my case with my biscuit cutters is actually pretty thin if you look at it from the bottom. From the top there's like a ridge, but the bottom, which is what we're really looking at here. Okay. All right, now if you look at the formula, of course, we're going to let the number of cylindrical shells that we're fitting in go to infinity. And so therefore we have thickness right here. We have the height. We have the radius right here. And that radius will be the distance from the axis to distance from axis of rotation to the shell. Cylindrical shell, I should say. Cylindrical shell. Sorry, my Y got weird there. There you go. All right, so distance from the axis of rotation to the cylindrical shell. And then we have our starting shell. So this is the innermost shell. Shell x value. To the outermost shell x value. Like that. Okay, so one more time. We're finding the volume by going from the innermost cylindrical shell to the outermost cylindrical shell. We take the surface area of the shell, multiply by the thickness, and we stack them up from A to B. Right, just remember my nesting biscuit tins. Of course, there is one complication I could throw in. Well, actually, there are a couple complications. What if it's not going to the region, sorry, is not touching the axis? So if you look at this one, I have that region touching the x-axis when we swing it around. But what if it doesn't touch the x-axis? Then what do we do? Well, it's still the same kind of concept. It's just we have to work a little bit harder for it, all right? So you still have your axis of rotation, right, spinning around up here. So you still have your rectangle right here, which is this same rectangle right here. It still has a thickness of dx, right? Delta x when it's finite, but dx when there's infinitely many shells, right? So the volume would be equal to, okay, So it's integral of 2 pi. It's still going to be r of x because that's still this distance right here, the radius. So it's 2 pi. It's going to be r of x. We're still going to have a starting point, an innermost shell and an outermost shell. So the innermost is at A and the outermost is at B. So we're still going to go from A to B. What's going to be different is the height. The height is going to be one function minus another function, because you're going to take f of x, which is this curve up here, minus g of x, which is this curve down here. So for example, if this curve up here was f of x, and this curve down here is g of x, then you would take, oh, let me do it in a different color blue. Sorry, I already used that blue for the sake of the radius. So it would be f of x minus g of x. Right? Dx. Now, one of the ways this method can be easier is you'll notice there's no squared anywhere. So it's not r of x squared like it was with the washer method. The squaring can sometimes make the thing difficult. But that said, it is everything multiplied by this radius, so you can get squared values in here, but it can sometimes be a little bit easier to set up, particularly when there are holes in it and when it's not touching the axis. This actually can be a bit simpler than the washer method, depending on the setup. So don't be afraid of the shell method. It's really just as easy as the washer method, but it's a different way of thinking about it.